Be solving lead code number 154, find minimum, but this is the second part. It is a hard question on lead code and it is the daily problem for today. Now before I start the question and the explanation, I would heavily suggest checking out the previous video, which was the first part, as the approach itself is very similar and there's only a small tweak that you have to make. But in this explanation, I'll be touching on about their follow-up question, the fact that do we think that the algorithm's time complexity will be the same or will it be different from part 1. So what did we do in part 1? We did a binary search, right? In part 1 we did a binary search and we were told that the elements were unique, in the sense that we will not encounter the same element again. And in this one we've been told that there is duplicates, there is a chance for duplicates to happen. Now the basis of the question is the same. They are explaining rotations in the sense that it is a circular shift, right? But the question itself can be summed up to just the fact that all you have to do is find minimum. Yes, the number of rotations correspond to the minimum, but finding the rotations, I haven't tried it, but it's probably a lot more complex than just finding the minimum using binary search or whatever, right? And I'm sure finding the rotations would probably be more than O of n, and you can do find minimum in O of n as well. Just find the minimum of nums. Now, for the question itself, in part 1, what did I emphasize? So in part 1 I emphasized the fact that, actually I'll consider a different example. Let's see, 2201. In part 1, right, I emphasized the fact that when we were sitting at middle, we checked at our right pointer, right? We saw that 3 was less than 5, right? And that would mean that the portion from 3 to 5, whatever the portion from 3 to 5, it could be 3, 4, 5, 3, 5, anything, it is sorted, right? In the sense that that portion is sorted. So that would mean that the minimum, right? The minimum, if you consider 3 to 5, then 3 is the minimum, right? Worst case scenario. But since it is sorted and we want to figure out this, there was this apparent part where the array goes up, it is sorted, then there is a fall in the value and then it's sorted again, right? So if we see that 3 to 5 is sorted, then where will we find this apparent fall, right? Well, it would obviously have to be in the left portion of the array, because we're trying to find minimum a. That's the first thing, we have to try to find a minimum. So it would be stupid to go to 3, 4, 5 to find the minimum when you should be going behind 3, because it might be a 0 rotated sorted array. Okay, so we will go 1, 3, 5. We'll narrow it down to 1, 3, right? We will still consider 3 to be a candidate of the minimum, right? Like I said, worst case 3 can be the minimum. So we will go back and we will search 1, 3. And when we do 1, 3, we will see this is the middle, this is the right. We would say 1, 3 is sorted, right? It could be 1, 2, 3 or it could be 1, 3. Doesn't really matter to us right now. So 1, 3, we see that it is sorted. So that would mean that we would bring our right counter back down again and we would end up with 1. And at the end we would just return our left pointer because that would correspond to the minimum. Now in this question, it is the same exact approach, except we just have to consider an extra case. Now, what is this extra case, right? When we were talking about unique, right, we completely ignored the idea of equality, right? I said we can have a less than 3, less than 5, right? We could have a 6 greater than 5, right? If it was greater, then we would go to the right of the array, right? But to encounter this special fall, right? If it was greater, then we would try to encounter this special fall by going to the right of the array. But I never considered the idea of equals, right? In that, I never considered the idea of equals. And given the fact that, it can be equal, how do we figure out which way to go? So the best way to think about it is, let's see, if we had some this is a rotated sorted array, we had some element x over here and we found the same element x over here, right? It would mean that there would be like a portion where it would sort itself, right? So we would essentially, what we would do is we would move our right pointer one behind to run the same binary search. Just to you don't even have to worry about the pointers, actually. Just do this. Just think that when we were sitting at x, right, and we found that the very rightmost value is also the same as our x, that means that, well, we should try to check the next value that might come up right after that, right? That's the only logical thing to do. Once you have hit an equal, you won't move your left pointer for no reason, right? Your left pointer is sitting at the very back. It's irrelevant right now. So what is the most logical move we should do? Move our right pointer back one to check it with a new value to see whether it would meet one of these two conditions over here, right? And that's it. That's it for this question. So all we have to do is, to the previous code from part 1, this is the same exact code. And like I said, if the one that we are sitting at, num's middle, right, is less than the num's right. If we're sitting at the middle that's less than the right, that means the portion ahead of us is sorted, right? The portion ahead of us is sorted, so why would we consider the one that might be increasing? No, right? We wouldn't be considering that. So what we would do is we would shrink it to the left half of the array. Now, the second case, that nums mid is greater than nums r, right? The one we are sitting at is greater than that. Then we want to encounter this one little fall that happens in the value. And where will we find that? Well, to the right of the array. And we won't consider ourselves, right? Because, well, we are essentially, we want to encounter a fall, not that we are we are one of the people that made it fall. Because if we are the one of the people that made it fall, then this condition would be true, because we would be like a minimum, right? So we will not consider ourselves when we're considering the right part of the array. Otherwise, that would mean that they're equal. If they don't fit on those two, that would mean that they're equal. And we would just move it one down to just try and see, okay, just check it with another pointer and return nums. But you look at this and you'll be like, okay, this might run in O of log n, right? But keep in mind what they have asked over here. They've said, would this affect the runtime complexity of the algorithm? And yes, it absolutely would. So if we consider an array, right? So let's say it had duplicates at the very end over here, right? We got some middle. Okay, so this middle will have to be the same as the right for us to put this up. But if we were essentially just given this, or we were given 0, 1 at the end, sorry, let's do 1 here, 0 here. So it was something like this. Originally, this is pretty much sorted already. This is a 0 rotated sorted array, and we have to find 0, right? So what we would do is, we would hit our middle, so 0, 1, 2, 3, 4, 5, 6, right? 6 by 2, 3, we will be sitting at our middle. And like I said, we would compare it to the right. We will go this, 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 until we hit this, right? And now we would check, again it's equal, so we would go back here. Then we would do 1, 0, 1, 2, right? We would sit at 1, and then we would check with 2. We would see that it is not, so we would make it 0, 1 now. And then we would be sitting on 0, 1, we would sit at 0. And at the end we would return nums L, right? Because we would partition this to 0. But you see what I did there? we've essentially checked every single element, right? We haven't done a splitting into half like binary search always would. We've done more of like a two pointer approach in this case, because we've done it in O of n, right? Because we've gone through these twos and we've seen, well, but there is no point, right? uh, we're just decrementing by one, and we've checked every value, and we'll come down to the last three, and that will also get partitioned into 0 1 and then 0. So we've checked every single element in the list. And what is checking every single element in the list? Well, that's O of n. So there might be a very minor chance that, not minor chance, sorry, it might be marginally better to do this algorithm than to do a min of the nums. But yes, it does heavily affect our time complexity from the previous approach.